So today we're looking at the law of sines again, and we're going to kind of build on what we started using the law of sines, and we're going to look specifically today at what's known as an ambiguous case. All right, and we're also going to look at cases where sometimes you get one that actually turns out to be impossible. Okay, and that's where some of the geometry facts that we've had in the past will come into play too.
What does oblique mean?
Oblique means not a right triangle. It's just kind of a generic term for a triangle that's not a right triangle. Okay, so that's kind of what we're dealing with here is oblique triangle trig, or you could just say non-right triangle trig. Okay. I want to look through this little chart. This is in the textbook. I thought was kind of helpful here, but it lays out different possibilities. Okay. Now, this isn't something that you have to memorize or something like this, but I do want to walk through a couple of these and highlight two of them in particular. Okay. First of all, the ambiguous case is the case where you're given two sides and an angle. Okay?
It's like a bunch of ants over here.
It is. Okay, but the... So let's look at these different cases. First of all, side-side angle. We already said that if you have two angles in any side, whether it's angle-side angle or angle-angle side, you can obviously figure out the third angle by just subtracting from 180, and you automatically will have a pair that are across from each other. Side-side angle, you will have a pair across from each other. As you can see here, A is across from A and angle A. You'll know both of those, okay? So here we're given sides A and B and angle A. So side-side angle, okay? The problem is this doesn't always work, and the other problem is sometimes when it does work, there's more than one possibility. Okay? Now, you will be able to figure out algebraically when it doesn't work because it'll give you something that's just impossible. Like it'll give you a negative angle, or it'll give you like a side that's, impossible or something like that. So, for example, on this first one here and on the next to last one here, you can see that, and we'll also look at kind of the logic here too. But there are some cases where it works, and then we see here this one where we have two different possibilities, okay? So let's highlight, first of all, the times when it does work, okay? One case is when it turns out that we actually have a right triangle. This side A that we're given right here actually equals the height, which means that this would be a right triangle. And that's going to give us one unique solution, okay? So that's a case that we can actually use. All right. Hopefully, if we recognize, though, that it's a right triangle, we're not using the law of sines. We just use SOHCAHTOA because it's easier. All right. Then we have this second case where I've already circled the A and the A. And this is where A is greater than B. Okay. If A is greater than B, you'll notice that happens both here and in the last one right here. A is greater than B. A is greater than or equal to B. As long as the side across from the angle you're given is bigger, then you know it's going to work. Okay? You know it's going to work. Where we run into a little bit of trouble is when A is shorter. Okay? Now, if angle A is obtuse, obviously you can only have one obtuse angle in a triangle, right? So I know that the side across from the obtuse angle will always be which one in the triangle?
Oh, the side.
the side,
It'll be longer.
it'll always be the longest, because an obtuse angle is automatically going to be your biggest angle, so your opposite side has to be the longest side. Alright? So in this case here, if A is shorter than B, and you have an obtuse angle, that's impossible. Okay? There's no way that you can do that. There's no way you can make a triangle like that. So there's no solution for that one. But also, even if A is acute, if A is not at least as long as the height, okay, which may or may not be that obvious, then you're going to get something impossible. Now let me just look at an example of that one real quickly here. Let's say that we have a side B that's 9 units long. Side A, let's say, is 3 units long, and this is 70 degrees. Okay, so this is an acute angle that we're given, and we're going to suppose that it's a triangle because we haven't been proven otherwise. All right, but let's look at this using the law of sines. Okay, if I were to try to find, we'll call this angle B down here in the corner, what angle would this be? I would do the sine of B over 9 equals the sine of 70 over 3. Okay? Now, I start to solve, so I multiply both sides by 9, and I get the sine of B equal to 9 times the sine of 70 over 3. And I get 2.819 and so on. Okay? Now, how do I know right now that this triangle is impossible to make?
Because the sine's maximum value is 1.
Exactly, Davi. The sine's maximum value is 1. That's why I said it's going to become very obvious pretty quickly in the process that something's wrong here. Okay? If you get this, then you automatically know, nope, there's no way I could have this kind of a triangle. Alright? There's no solution to that. Okay? This is why, again, we call this side-side angle case the ambiguous case, because sometimes it works, sometimes it doesn't, and then,
If you don't memorize it, you just gotta try it out.
yeah, you're not gonna be told what the height is. So you're not gonna know whether A is shorter than the height or not. So you just gotta try it, and be aware that, yes, it's possible to run into this case, and really just anytime you're given two sides and the angle and you're using the law of sines, you're just, you should have your antenna up and be more aware, just look for strange things to happen. Okay? Now, we have this case here where there are two possible answers. Okay? There are two possible answers. This can happen because first of all, A has to be acute. If you have an obtuse angle, remember, we know how to deal with that. Okay? But if A is acute and A is smaller than B, okay? So in other words, the side that you're given across from the angle that you know is shorter than the other side that you know. Okay? It's possible to have two different answers. Now, let's look at an example of this one. Okay? Let's say that we know this side here is, say 12. And let's say we know this side here, or this angle right here, is say 30 degrees. Okay? And we know the side across from the 30-degree angle is 7. Okay? Now, because I don't know how long my third side is, I could have an obtuse angle right down here at B, and 12 could be the longest side there, all right? Or the other alternative, I'll call that B1, the other alternative is that this side 7 here goes out this way and angle B is acute. Alright, I'll call that B2. Alright, and you might say, well, how in the world does that happen? Let's look at it algebraically, using our law of sines. Okay? If I were trying to find angle B, I would have the sine of angle B over 12 equals the sine of 30 over 7. Very good. Okay? So I multiply by 12. And I get the sine of B to equal 6/7. Okay? Sine of 30 is a half, times 12 is 6, 6 over 7. Okay? Now, question. You find this on your calculator, hitting inverse sine of 6/7. What does your calculator give you? Make sure you're in degrees.
59 degrees.
What?
59 degrees.
59 degrees?
Well, 58.99, whatever.
Okay.
Yeah, 59.
So we'll go with 59 degrees. That's good. 58.99. So what others got?
Yeah.
Same thing? All right. So that would be this right here. Now, let's think about this. Is there anything that is mathematically impossible from what we have so far? Okay, well, 30 is smaller than 59, so look across from 30 and we have 7. Look across from 59, it's 12. That's possible,
Did you?
okay? But sine is positive not only in the first quadrant, but it's also positive in the second quadrant. If 59 were our reference angle, what would that other angle equal?
31.
121, okay?
Oh.
Or 121 degrees. Well, guess what? If I had 121 degrees right here, is there anything mathematically that would contradict or make that impossible?
No.
Well, let's look. 121 is bigger than
No.
30, so 12 is bigger than 7. That makes sense. Here we actually have two completely possible triangles that we could make using a side of 7 across from an angle of 30 with a side of 12. Okay? And it's not that there's anything wrong here or we did anything wrong, it's just there are literally two different possibilities of how I could have done that. Okay? Does that make sense?
What would you add to 59 to get the other side?
To get the other angle?
Yeah.
You'd have to actually look at it as two separate as two separate triangles. Like if we had it where this was 121 and that's kind of ugly. All right. That would be 30 and this would be 12 and this would be 7. So 121 plus 30 is 151, which means we have 29 degrees that would go up here.
Subtract it from 180, right?
You would subtract it from 180. The other one, and by the way, this is where you might run into a contradiction, okay? But if we had 12, 7, 59, and 30, you subtract 89 from 180 and you get
Okay, why wouldn't you just do
91.
Why wouldn't you just do the other part of the angle? Triangle.
What do you mean the other part of the triangle?
Like it's like one and then the other one, but you just did that full one.
Well, basically what I did is I took this diagram and this triangle, I just redrew over here by itself. And then this whole triangle, I redrew over here. You wouldn't really look at
Oh yeah,
this.
that's okay.
Okay, that's what you're asking. Yeah, this one isn't going to be as useful there. Okay, so we have two different possibilities. If you continue solving, you're going to get two perfectly valid solutions for what this bottom side would be. Okay, you may get a solution at that point that messes up our longest side across from the longest angle, or shortest side across from shortest angle, and in that case then you could identify, oh, that must be wrong. Okay, but the reality is you actually can have two perfectly valid possibilities. Okay, that's why this is called the ambiguous case. Ambiguous just means unclear. Alright?
Couldn't you tell from the diagram?
If the diagram is drawn to scale, yes. But often we don't have a diagram, or we're told, hey, this diagram isn't necessarily drawn to scale. Or, think about it like this. What if that angle was like a 92-degree angle? How could you tell just by eyeballing whether it's 92 or 88? You know? I mean, maybe if you got a perfect right angle and held it up there to see. But even then, you know, don't just trust what it looks like. Trust the math. Okay? Alright, so we have this ambiguous case. We have different possibilities. And I don't want you to, you know, get freaked out with this just thinking of this all the time. But it's just something when you're given side-side angle. Okay, if you're given side-side angle, that should just kind of put you on the alert. You know, hey, I need to pay attention and look out for these different cases. Okay? Don't try to memorize this whole table. It's really not worth it. Okay? Alright, so the next thing we want to look at, we have the ambiguous case, and then we have this extension. This extension here of the law of sines is our area formula. We're going to learn two new area formulas. This one I'm pretty sure you have never seen before. The other one you may have seen in geometry class. Okay? But the other one we're going to wait to look at a little later. So let's think about this problem here. How could we find the area of this triangle if we know area is base times height divided by 2?
You gotta find height, but you can do, you can like cut it in half and do diagram here, can't we?
Okay. How would we cut this? Use it like cut it in half here.
From B 40, yeah, just make it 90 degrees from B.
Okay, good. Make it 90 degrees straight down from B. Because that would give me the height, right?
Mm-hmm.
So now I know that my area would be 10 times the height divided by 2, right? Base times height divided by 2. Okay? So now we got to figure out our height. How would we figure out the height?
Is it a formula that's L radical 3 over 2? Or is this just for 60, 60, 60?
No. This isn't just for a specific kind. I think that might be for 60, 60, like an equilateral triangle.
Wait, didn't
Um,
we use height to like derive the formula that we use now, so we can like reverse that?
Okay.
Or am I
So let's keep going with that idea.
off?
You can say that the sine of 50 equals h over
Sine of 50 equals h over 12. That's right. If I'm looking at just this left-hand side of the right triangle, then I can use opposite over hypotenuse. H over 12 is sine, right? Everyone with us? Okay. So, we multiply by 12. And h equals 12 times the sine of 50. Whatever that is. So guess what? My area, I can now plug that in. Area equals 10 times the height, 12 times sine of 50, over 2. Okay? Now I just punch it into my calculator.
45.386.
You say 45 or 25?
45.
45.386, 396.
No, just 96.
Oh, 0.96. There we go. 45.96. Okay, and we'll go 2 decimals just like we do for the lengths of sides. All right, and this is an area, so we don't have a given unit, so I'll just say units squared. Okay? So, pretty cool. We were able to figure out the area using some right triangle trig. Okay? If you remember, this was very similar to how we derived the law of sines. Okay? We used that height, we divided it into a right triangle, and so on. Okay? Now, the reason why I show you that is because we can generalize this process. Notice what we were given. We were given 2 sides and the angle between those 2 sides. In other words, side, angle, side. Okay? If we do that, we can use what I call, this isn't like a formal name for it, but I call this the Sas Area Formula, okay? So Sas Area Formula, you'll notice we end up doing 1/2, because 1/2 base times height, right? 1/2 BC sine of A. Or using this right here, the base would be B, and you'd have A times B times the sine of C. Okay, so this is kind of what we would have for this one, okay? So area equals 1/2 AB sine of angle C. Okay? This is the same thing that we did on that previous problem here. We had 50 degrees, you had 12 up here, and you had 10 down here. You ended up doing 1/2 times the 10 times the 12 times the sine of 50. Okay? 1/2 times the side times the other side times the sine of the angle between them. Yes?
So why would you use something like this if you just do an extra step to get the height and then just plug it into the other formula?
Because you don't have to. This finds the height for you.
Well, yeah, but it's just a one step that you're taking out.
Yeah. Let's say you do this 100 times and you're saving yourself 1 step every time you do it. Right?
Yeah.
You know? It's just a way of streamlining a process. We don't care what the height is. We just want to find the area. Okay? Now, if we wanted the height, then yeah, we would definitely could do that. And by the way, that's partly why I show you where this comes from, where this is derived from. It's a pretty simple derivation, but it's related back to the right triangle trig and finding what that height would be. Okay? So we could do just a quick example of this here. Let's say that we were given that this side here is 18, and this side here was 9, and this angle here was 45 degrees. Okay? If we wanted the area of this triangle, what would we do?
18.
1/2 18 times 9 sine of 45.
Good. 1/2 times 18 times 9 times the sine of 45. And we don't even need a calculator for this one. Okay. Okay, so we've got root 2 over 2, right? For sine of 45. 1/2 of 18 is 9. 9 times 9 is 81. So 81 times root 2 over 2, and you could do, if you wanted to do 40.5, or just make that 81 root 2 over 2, that would work.
I have a question.
Square units. Okay, and that would be the exact area. If we punched it into our calculators, then we could get an area that we could round. Okay? Yes?
Would there be like two possible areas? Because sine is positive in both quadrants. So like the sine of 50 could be one thing, but it also could be another. So would we get two areas?
Well, hang on. When we're you only get the two possibilities when you're solving for the angle. When you're doing an inverse sine.
Oh.
Okay? Here, we're told the angle is 50 degrees, or in this case, the angle is 45 degrees. So there's no other possibility.
Okay.
If we were given side-side angle and solving for an angle, then yeah, we might have two possibilities. Okay? Any other questions? All right. It's relatively straightforward. So I've given you a number of practice problems here at the end. Okay? Let's focus, please. I've given you a number of different practice problems here at the end. Not all of these are in the required IP, but I've given you a few different word problems in the required IP that you can try, that you need to try, and then there are additional ones here that you can try if you need some more practice, okay? All right.